Hello, I'm Dr. Sigarkanti, Associate Professor of Mathematics, Government First Grade College, Care from Bangalore. In this video, we go for some more basic concepts of graph theory. Uh, bipartite graph, bipartite, bipartite graph. So that is a graph G is said to be bipartite if the vertex set V of the graph G, if the vertex set V of G can be divided into two subsets, say V1 and V2, such that no two vertices in V1 are adjacent and no two vertices in V2 are adjacent. Or we say that like this also, that is every edge of G joins a vertex of V1 to a vertex of V2. Okay, like this also we can say. Examples. We write an example here. G, take 1, 2, 3, A, B, C. See, this is a bipartite graph. Okay. So here this is one set V1 and this is another set V2. We have divided the vertex set into two subsets such that no two vertices in V1 are adjacent and no two vertices in V2 are adjacent. That is, if there is an edge, it must join a vertex of V1 to a vertex of V2. We say that this is a bipartite graph. Similarly, we can define tripartite also. Then we have to make divide that vertex set into three subsets V1, V2, V3, and no two vertices in V1 are adjacent, no two vertices in V2 are adjacent, no two vertices in V3 are adjacent. So this is bipartite graph. And here this is our set V1. Here 1 is adjacent with two vertices of V2. 2 is adjacent with two vertices of V2. And 3 is adjacent with only one vertex of V2. And suppose if every vertex of V1 is adjacent with every vertex of V2, then we say that it is a complete bipartite graph. And suppose this V1 consisting of m vertices and V2 consisting of n vertices, if this is a complete bipartite graph, then we denote this by k, m, comma, n. So that is some examples on complete bipartite graphs are, we write k, 2, 3. Means here, two vertices are here, three vertices are here. We join these vertices with these vertices. And this is adjacent with, this is our K23. Similarly, K33 is nothing but three vertices in V1 and three vertices in V2. Every vertex of V1 is said to join every vertex of V2. So that is here, I'll join this. join this, joining this, joining this edge, this edge, this edge, this edge, this edge. So this is our K33. This is known as complete bipartite graph. So in general we write KMN, means here we have M vertices and here we have N vertices. Every edge, every vertex of V1 must be adjacent with every vertex of V2. Then we say that it is a complete bipartite graph. Otherwise just we say that it is a bipartite graph. Okay. Next we define one more term in graph theory, that is a tree. Tree. Definition of tree is uh, connected, 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 a cyclic graph is defined, is defined as a tree. So already we have defined what is connected graph. Connected graph means if every pair of vertices are joined by a path, then you say that it is a connected graph. Acyclic means having no cycles. See here, if I consider a graph here, this is a graph having cycles. Okay, because there is a cycle here. So I have to write a connected graph without cycles. So we write here T1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Many more we can write here. So that is here. This is a tree. This is a connected graph. Okay. This is a connected graph. And no cycles are there. No cycles are there. Therefore, we say that this is a tree. Okay. And we write one more graph. This is also a tree. Connected graph having no cycles is defined as a tree. And this looks like a tree. Therefore, we call this as a tree. And if many trees are there, then we say that it is a forest. That is, we have to delete this term. If I remove this connected from this definition, then this becomes a forest. That is, an acyclic graph is defined as a forest. Okay, next we define forest. Forest definition: an acyclic graph is defined as a forest. An acyclic graph is defined as a forest. For example, T1. This is the forest here. So here we have, this is one part, this is one part. And we say that this maximal connected graph is a component of this graph. So that is, we have two components here. This is one component and this is another component. Therefore, we say that this is a forest. This is a disconnected graph having no cycles. Therefore, we say that it is a forest. Okay. Then we define path graph. Path. So path means it is nothing but consisting of only one path. So that is here. One path means uh, all the two vertices having degree 1 and all remaining vertices having degree 2. We say that it is a path. So that is here. Path is this. Okay. So we say that this is a path. And here uh, path is nothing but a tree. Okay. Every path is a tree. But every tree need not be a path. Every tree need not be a path. Okay. So this is the path. And next we define wheel. Wheel. Wheel is nothing but a graph having a vertex, one cycle here. 1, 2, 3, 4, 5, 6. Okay. Maybe many vertices here. We have to write a cycle, and in between, in the middle, if I write one vertex and join this vertex with all the vertices on this cycle. So that is this. So this is defined as a wheel graph. Okay. So that here we have how many vertices are there? 1, 2, 3, 4, 5, 6, 7. Okay, 7 vertices are there. We denote this by W7. Okay, and here this path is denoted by P. How many vertices? 1, 2, 1, 2, 3, 4, 5, 6 vertices are there. Therefore, we denote this path by P6. That is P6 is a path with 6 vertices. W7 is a wheel with 7 vertices. So that is their uh, W4 is nothing but, so this is our W4. And this is the smallest wheel. W4 is the smallest wheel. W5 is, this is W5. Okay. This is a wheel with 5 vertices. And W6 is around this, if you write a cycle with 5 vertices, and in middle we, if you write one vertex, joining this vertex to all the vertices. So that is our W6. Okay. This is a wheel graph. And we define star star graph, or just we say that star. So that is here K1n is defined as a star. That is complete bipartite graph. V1 consisting of one vertex and V2 consisting of n vertices. So for example, if I consider uh, K13, so one vertex here, 3 vertices are here, I'll write like this. This is our K13. We call this as a star graph. This is because if I write this graph can be written like this. Okay, this looks like a star, therefore we say that this is a star graph. Similarly, K14 is nothing but 1, 2, 3, 4. Or we write 1, 2, 3, 4. This is our K1n. Okay, this is our K14. So in general, we can define star graph. So that is here in V1 consisting of one vertex and V2 consisting of n vertices. Then we say that it is K1n. This is defined as a star graph. That is here every star is nothing but a bipartite graph. But every bipartite graph need not be a star. Okay. And we have some graphs here. Uh, regular graph. Regular graph. Regular graph. So that is if degree of each vertex in a graph G equal to say R, then G is called R regular graph. Okay. So if the degree of each vertex is R, then we say that it is a R regular graph. Then what is a two regular graph? That is here two regular graph. Every cycle is a two regular graph. So that is we consider C3. This is our C3. And this is a two regular graph because here degree of each vertex is equal to 2. Similarly, C4. This is also a two regular graph. C5. 1, 2, 3, 4, 5. This is also a two regular graph. That is every cycle is a two regular graph. Okay. And what about three regular graphs? Three regular graphs. I will draw some three regular graphs here. what I do here is I write a cycle with three vertices and one more cycle again with three vertices. Okay, and I will join these vertices. Okay. So this is a three regular graph with six vertices because degree of this is 3, 3, 3, 3, 3, 3. Okay. This is a three regular graph. Similarly, we can draw four regular graph. So that is here. We write C4. Outside also we write C4. Okay. Then joining these vertices. Right. So this is also a three regular graph. This is how many vertices are there? 8 vertices are there, and degree of each vertex is equal to 3. Therefore, this is known as this is a three regular graph. And here, three regular graph is defined as a cubic graph. So that is three regular graph is called cubic graph. Cubic graph. Degree of each vertex equal to uh, 3. We draw some examples here, some graphs here. We write 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, joining these vertices. So this is the three regular graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 vertices are there and degree of each vertex is equal to 3. Okay. So therefore we say that this is a cubic graph with 10 vertices. And one more cubic graph with 10 vertices. We write this as uh, 1, 2, 3, 4, 5. Outside 1, 2, 3, 4, 5. First I will draw this cycle. Okay. And then we draw one more cycle here. Okay. And joining these vertices. Yeah. This is also a three regular graph. Here we have 1, 2, 3, 4, 5. 5 vertices are here. Sorry, 5 outside and 5 inside. Total 10 vertices are here. And degree of each vertex is equal to 3. Okay. Degree of each vertex equal to 3. Therefore, this is a cubic graph. And this graph is known as Peterson graph. This graph is defined as Peterson graph. And note that these two having 10 vertices and degree of each vertex is equal to 3 and number of edges are also same, but this graph is different from this graph. Okay, so that is these two graphs are not same because see, just if we observe, there is a square. C4 is here. Okay, C4 is here, but I think there is no C4 here, so it is not possible to find C4. So therefore these two graphs are different graphs. Both are cubic graphs, but these two are different graphs. Number of vertices same, number of edges are same, degree of each vertex is same. Even then, these two graphs are different graphs. These two are not isomorphic. I will define afterwards that what is that isomorphic. Okay. Next, I will go for. So if I write, usually we write like this. PQ graph. PQ graph. That is a graph with P vertices and Q edges. We call it as a PQ graph. So that is here a graph with P vertices and Q edges is defined as a PQ notation. PQ graph. Right? Number of vertices equal to P, number of edges equal to Q, then you say that it is a PQ graph. We write this as a P comma Q graph. say 2 comma 3 graph. 2 comma 3, that is 2 vertices and 3 edges. Is that possible here? 2 vertices are there. If I am in a simple graph, so that is without multiple edges. 2 vertices are there and I have to write a graph with 3 edges. I think this is not possible. Suppose if I write 3 comma 2 graph, that is 3 vertices. 3 vertices are there and 2 edges. I think it is possible. Okay, this is possible. This is a 3 comma 2 graph. Can we get a 3 comma 3 graph? Yes, I think 1, 2, 3 vertices and 3 edges. Yeah, this is a 3 comma 3 graph. Can we have 4 comma 5 graph? 4 vertices and 5 edges. Let me try. 1, 2, 3, 4. 4 vertices. 5 edges. You can write in any manner. This is 3. Okay. I added 3. One more edge. Another 2 edges I have to add. I will add this and I will add this. Okay. This is a 4, 5 graph. 4 vertices are there. 5 edges are there. Can we get 4, 6 graph? Yes, I think. So just this is a graph with 4 vertices and 5 edges are there. Just we add these two non-adjacent vertices. This is a 4, 6 graph and I think it is not possible to get 4, 7 graph because all the edges. So we all edges are existed here. It is not possible to add one more edge to this graph. Then that becomes a multi-graph having multiple edges. If I am drawing a simple graph, if 4 vertices are there, then maximum number of edges is equal to 6. And here, if a graph is there with p vertices, then how many, that is what is the maximum number of edges allowed in a simple graph with p vertices? For that, I have I want to calculate the number of edges, the maximum number of edges in any graph. So if I consider, say, KP, or in particular, I will consider 3, K3. So here, K3, how many edges are there? 3 edges are there. Okay. In K4, this is our K4. Okay, number of edges 1, 2, 3, 4, 5, 6. So here we have 6 edges are there. How to calculate this? Suppose we have, okay, 10 is there, then I have to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I have to add each vertex to all other vertices. Okay, then how to find the number of edges in this complete graph? See here, for this K10, if there is a vertex and 9 vertices are here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So total 10 vertices are here. And in K10, complete graph with 10 vertices, according to the definition, every vertex is adjacent with every other vertex. So that is here, this is adjacent with all other vertices. Okay. So that means here, this vertex is adjacent with 9 vertices. Therefore, what is the degree of this vertex? The degree of this vertex equal to 9. Similarly, we are in K10, that is complete graph. Therefore, this also must be adjacent with every other vertex, that is 9 vertices. Degree of this is also equal to 9. Similarly, degree of this equal to 9. Degree of this equal to 9. So, that degree of each vertex is equal to 9. And the total number of vertices here are 10. So what is the sum of the degrees? In this case, sum of the degrees is equal to twice the, and we have the formula, twice the number of edges. What is the sum of the degrees? Number of vertices are 10 and degree of each vertex equal to 9. So that is 10 into 9 is equal to 2 into Q. This implies Q is equal to, Q equal to how much here? 10 into 9 divided by 2, 2 into 1, 25. This is equal to 45. So in general, Kp is there. That is complete graph with p vertices. What is the degree of each vertex in Kp? Degree of each vertex equal to p minus 1, because Kp, this is a complete graph with p vertices. Therefore, every vertex is adjacent with every other vertex, means degree of each vertex equal to p minus 1. Then, what is the sum of the degrees? P vertices are there. Degree of each vertex equal to p minus 1. Therefore, sum is equal to sum of the degrees equal to p into p minus 1. This is equal to twice the number of edges we have. And this implies q is equal to p into p minus 1 divided by 2. So this is the number of edges in a complete graph. And the complete graph consisting of maximum number of edges, and any other graph with p vertices must have the edges less than or equal to this, that is less than. If it is not Kp, then definitely the number of edges must be less than p into p minus 1 by 2. So therefore we can write here any graph with p vertices, any graph with p vertices, q is less than or equal to p into p minus 1 by 2. So that is here number of edges always less than or equal to p into p minus 1 by 2. And if this g is equal to kp, then equality holds. That is q becomes p into p minus 1 divided by 2. So this is for complete graph. And for any graph, any graph with p vertices, number of edges always less than or equal to p into p minus 1 by 2. Okay. Now we define some more concepts in graph theory. We write independent set. So that is here, let g equal to p comma e be a graph, then a subset, say I will take S of vertex at V, is said to be independent if no two vertices in S are adjacent. Okay. So that is, we take S as the subset of the vertex set. If no two vertices in S are adjacent, then we say that this set as independent set. I will go to an example to explain this concept. So take a graph G. Okay, this 1, 2, 3, 4, 5, 6, 7, 8. So here 8 vertices are there. V consisting of 8 vertices. Let me consider S1 equal to, just if I take only one vertex here. Is this independent? Definitely. That is, every singleton set of vertices is always independent. And if I take, this is independent. And if I take S2, if I take 1 comma 7, is this independent? Yes, because 1 is not adjacent with 7 here. So that is here, the no two vertices in S2 are adjacent. Therefore, this is also independent. Next, I will go for S3. S3, I will go for uh, 1, 1, 4, 5, 7, 8. Is this independent? I think yes. 1, 4, 5, 7, 8. No two vertices are adjacent here. 1 is not adjacent with 4, 5, 7, 8. 4 is not adjacent with 5, 7, 8. 5 is not adjacent with 7, 8. 7 is not adjacent with 8. So therefore no two vertices in S3 are adjacent. Therefore this is also independent. Now if I consider S4, 1, 3, 7, 8. Is this independent? No. Because see here 1, 3 are adjacent here. So that is here. These two vertices are adjacent. Therefore, S4 is not independent. So this is not independent. This is not independent. Okay. Now we'll consider some more examples on independent set. Okay, let me write one more. This is a graph. Okay. 1, 2, 3, 4, 5, 6, 7. So here we take S1 equal to 1. Definitely this is independent. And next S2 equal to S2 equal to. I will add some more vertices to this. Okay. So one I have taken here. Take a vertex which is not adjacent with 1. I will take, I can't take 2, I can't take 3. I will take 4 here. I will take 4. Okay. Next I will go for S3. I will keep these two vertices as it is. I want to add some more vertices to this. Okay, I will take 1, 4. I will take 6. Is this independent? Yes, because no two vertices in this set are adjacent. 1 is not adjacent with 4. And 4 is not adjacent with 6. 6 is not adjacent with 1. Okay. So this is our, these three sets are independent. And we go for S4. I take 1, 4, 6, 7. Again, I think this is independent because no two vertices in S4 are adjacent here. This is a independent set. So I have started with S1. I have taken only 1. And I am go on adding some more vertices to this set. 1, 4. And then I have added 6. And then I have added 7. All these sets are independent sets. Now, can we add some more vertices to this S4? So what are the remaining vertices here? 2, 3, 5. Okay. So these three vertices are remaining. Can we add 2 to this S4 so that the resulting set is independent? Now if I add 2 to this, then this will lose the property of independence because 1 is adjacent with 2. So I can't add 2 here. Similarly 3. Can we add 3 so that this resulting set is independent? No. So if I add 3 here, 3 is adjacent with 1. Okay, so therefore I can't add 3. Can we add 5 here? If I add 5, then 5 is adjacent with 4, 6, 7. So therefore it is not possible to add some more vertices to this set. So all the 4 sets are independent sets, but this set is something special. So here for these 3 sets, it is possible to include some more vertices without altering, without disturbing the property of independence. But here for this set, if I add any one vertex to this one, then it will lose the property of independence. Such independent sets are known as maximal independent sets. So in this case, S4 is maximal independent set. S1, S2, S3 are just independent sets. So that is here S4 is maximal. So like this we define maximal independent set. Maximal independent set. We consider some more examples on independent sets. Say I'll take K1, say 5. 1, 2, 3, 3, this 4, 5. So this is our 1, 2, 3, 4, 5, 6. Okay. Now if I take S1 equal to 1, is this independent? Yes, because every singleton set is independent. Now can we add some more vertices to this set by without disturbing the property of independence? I can't add 2 because 2 is adjacent with 1. I can't add 3. I can't add 4. I can't add 5. I can't add 6. So therefore here this is the maximal independent set. Now if I go to S2, if I take 2, is this independent? Yes. And S3, I take 2, 3. Is this independent? Yes. And S4, I take 2, 3, 4. Is this independent? Again, yes. S5, this is equal to 2, 3, 4, 5. Again, this is independent. Okay. Now S6, 2, 3, 4, 5, 6. Again, this is independent. Then to this set, I can't add any more. Only one vertex is remaining here. One is remaining here. So if I add, include one to this set, then this will lose the property of independence. Therefore, here S6 is maximal independent set, and S2, S3, S4, S5 are just independent sets. S6 is maximal independent set, and S1 is also maximal independent set. So here in this case, S1 is maximal independent set and S6 is maximal independent set. S2, S3, S4, S5. These are just independent sets. Okay. So this is about the independent set and the maximal independent sets. So okay. Thank you. I will stop here.